Hello AP Physics students, this is Mr. Everly talking to you. Not talking to you from Canada, this is actually recording, unfortunately. I want to show you something today about RC circuits. RC circuits aren't easy and they're kind of wild, and I thought it might be a good idea to have a video to explain some of this stuff. The first thing I want to show you is a circuit, and I took this diagram right from the book. It's a very simple diagram. What's happening here is we've got a battery, we've got a resistor, and we've got a capacitor. Now you can imagine if we take this switch here, imagine this is like a little door that can move. If I were to take this switch and connect it, I've got a connection here between these 2 points, and charge from the battery can begin to flow to the capacitor. And notice in this case the battery's positive side is charging this side, and the battery's negative side is connected to this end of the capacitor. So the capacitor will begin to get a charge. Now imagine that you start piling charge onto the positive side and onto the negative side of the capacitor. Pretty soon the charge itself is going to prevent further charge from coming through. That is, these are little negative guys. Adding more negative takes more and more effort, and pretty soon this thing is going to reach its maximum charge. Maximum charge, by the way, is called Q naught throughout this entire derivation, so keep that in mind. Whether the capacitor is discharging or charging, Q naught is maximum charge. Now, if we take this switch and we switch it to B, what we've done is we've eliminated the battery from the circuit. The battery is no longer connected, and basically the positive side of the capacitor is connected to the negative side, and it's going to discharge through the resistor. And kind of the reverse thing is going to happen. First, it's going to happen really fast because the positive side here, these positive, are just hate each other's guts and want to get over to the negative side. But that rush of charge is going to begin to trickle down, start to slow down after a while. So the rate at which the current is flowing is going to decrease, and it's going to decrease exponentially. So imagine as it's charging up, the charge on the capacitor is going to increase exponentially. So charge per unit time, it's going to start off at 0 and reach a maximum value. Call it Q naught. And then when we discharge it, it's going to start at Q naught and decrease, and that decrease is going to be also exponential. Okay? The thing is, the rate at which the charge flows depends on how much charge there is. So in other words, dq dt is dependent on Q, the very thing that's changing. So it's kind of a weird relationship. So how do you deal with this mathematically? How do you work this? The first thing we're going to do is look at a system where the capacitor is discharging. That's a little bit easier math, so we'll start there. So imagine we've got our situation where, okay, we put the switch in this situation, the capacitor is fully charged. As soon as we flip the switch, this thing discharges like mad. Now in this situation, we can use Kirchhoff's laws to write an equation for it, and we could say, all right, the potential difference across the capacitor as we go through the circuit is going to be Q over C. And that kind of makes sense because C is Q over V, so the voltage drop, or excuse me, the voltage gain is going to be equal to Q over C. Kind of makes sense. Just like before, this is going to be minus IR as we imagine current is flowing through the system. So if I follow this around using Kirchhoff's laws, I'm going to get the increase here at the capacitor as Q over C. I've got the voltage drop across the resistor, and I've made it back around the circuit, and according to Kirchhoff, that should equal 0. Now, if that's true, then Q over C is equal to I times R, or I is equal to Q over RC. And it's the first time we see this RC, which is kind of a special thing in these circuits. It's a special constant, which we'll discuss later. Now the current is decreasing, so I can also write that I is a rate of change that is eventually decreasing. So what I've got here is dq dt equals negative q over rc. So the rate of change of charge, the rate at which charge flows, called current, is equal to q over rc. I throw the negative sign in to indicate that it's a decreasing value. Now the next step, I need to separate the variables because I'd like to integrate this puppy, and my job first is to get this q over to this side and the dt over this side. So here we go. Oops, I messed up. Sorry. dq over q equals negative dt over rc. And just like in your notes, I'm going to integrate both sides. I'm going to attempt to come up with an equation which shows how q is changing. Alright, so if I integrate this thing, what I notice right off the bat is on this side I have a natural log of q. What I notice on this side is that r and c are both constants. So what I've got is minus t over rc plus a constant. Now we use c as a constant in calculus all the time. Unfortunately we're using c as capacitance, so I'm going to say k instead. We got to get rid of k, and we know that at t equals 0 the charge is equal to the maximum charge, the initial charge of the capacitor. So if we put those numbers in, put 0 in for t and put q naught in for q, what I've got is natural log of q naught is equal to k. Which means if I go back to my original equation here and rewrite it, instead of having a k here, I'll have a natural log of q naught. But imagine I could subtract that from both sides, and knowing the properties of logarithms, I can say natural log of q over q naught is equal to negative t over rc. Okay. My next step is to raise both of these guys to the power of e. Now I can do that, that's still legal, and I'm just going to push this up a little bit here. I think you can still see that on the camera. Raise this to the power of e, and I've got q over q naught. Raise this to the power of e, and there I have it. Rearrange slightly, the charge at any time is equal to the maximum charge, the fully charged capacitor, times e to the minus t over rc. So this is the equation of the charge on a discharging capacitor at any time. Now this little RC guy here is actually kind of a special thing. We're going to have a special symbol, a little tau, and that's equals RC. Now believe it or not, you can prove it to yourself that the units of ohms and the units of farads, when multiplied together, give you units of seconds. And I challenge you to, for a few seconds, figure that out and prove to yourself that it's true. Now, when this time rolls around, when this particular special time called RC rolls around, the capacitor is at a particular state of discharge. So let's go ahead and do that. We'll say, all right, at t equals RC, then our equation becomes q equals q naught e to the negative 1, because we've got RC on top and RC on the bottom. Now, if you punch that in, what you get is q equals 0.37 q naught. And at first you say to yourself, well, who cares? Well, it's about 1/3 charge. It's when 1/3 of the charge has moved, well, 2/3 of the charge have moved off the capacitor. We've got about 1/3 left. So 0.37, a little bit more than 1/3 of the charge is left on the capacitor. So it's kind of a special time for a capacitor. We all have special times in our lives, and that's a special time for a capacitor when t equals RC. It's called the RC time constant. Another special time, just like a radioactive isotope, you could think of, since this is exponential decay, we can think of its discharging as having a half-life. So you could say, hey, when Q equals 1/2 the maximal charge, we can set up our equation again, go back up here, replace Q with 1/2 Q naught, and we can figure out what's going on then. Okay, so in that case, we do a wah, and we say, hey, look, 1/2 is equal to e to the minus t over rc. Now, if I take the logarithm of both sides, I got the natural log of 1/2 equal to minus t over rc. Okay, or t is equal to minus rc natural log of 1/2. Okay, what that turns out to be is rc is tau, right? Natural log of 1/2 is actually a negative number. It turns out to be 0.693. Okay, so the half-life of this thing occurs, that is, Q is equal to 1/2 the maximum charge at 0.63 times tau. I said that slightly wrong, didn't I? 0.693 times tau, where tau again is that RC time constant. Okay. Other thing we note is that I, the current, is also decreasing exponentially. So in other words, we're going to start off with a pretty high current, and this thing's going to tail off, as mentioned before. So I, as we know, is equal to negative dq dt. So if Q is equal to Q naught, e to the minus t over rc, as we said before, then we can take the derivative of this thing, and it's right there in your notes. Taking the derivative means we're going to say dq dt is equal to negative Q naught e to the minus t over rc times negative 1 over rc, using the chain rule. This guy here is just current. Q naught over rc, the negatives cancel out, Warson. Q naught over rc times e to the negative t over rc. Okay, again, the top is units of charge, the bottom has units of time. It turns out that this is the initial current, the current that starts off when this thing is first starting to discharge. So the current starts out big, decreases exponentially. So this is the current of a discharging. It's also the current of a charging capacitor, because you can imagine when the capacitor charges up, first the current's really high. There's no charge on the thing. It's easy to put charge on it, and then the current begins to tail off as we add more and more charge. So this actually works for both charging and discharging capacitors. Now you have the notes in front of you for what happens when we're charging a capacitor. So that I don't make a 45-minute video, what I'd like you to do is take a look at my notes and see if you can work your way through the derivation for the charging capacitor. If you do that, what you end up with is that for a charging capacitor, Q is equal to Q naught 1 minus e to the minus t over rc. Okay. Again, this still works for current. Once again, when the thing is charging, you have to think of this as the maximum charge. The Q naught is a little bit deceptive because you kind of think of it as the initial charge. Well, the initial charge is 0, so that doesn't make any sense. So when it's charging, we think of this, okay, this is what it's going to reach. This is the maximum charge, and then this here gives you the fraction of the maximum charge it happens to be at time t. All right, so take a look at the derivation. The next thing I want to show you is a quick example, and this example actually deals with a charging capacitor, so it's probably a good one to do right now. So let's see if I can find my page here. It's right here somewhere. There we go. Okay, you have this in your notes, and what we're going to do is just take a look at a couple of these parts and see if we can make sense of this. The first one says, find the time taken for the charge to rise to 90% of its final value. You say, oh man, okay, so you've got this in front of you. I don't have to keep it on camera, I hope. Might be nice to keep the diagram there. But here's our equation for a charging capacitor, which you're going to look at the derivation on your own. So we're going to say when Q equals 0.9 Q naught, when it reaches 90% of its maximum, what time is it? Okay, we can do that. 0.9 Q naught happens at what time? Okay. Well, the first thing we notice is, wah, lose the Q naughts. Then we rearrange this thing. Notice now we can lose the parentheses and throw this to the other side. So what I've got here is negative 0.1 is equal to negative e to the minus t over RC. Lose the negatives, Warson. And if we take the natural log of both sides, I've got the natural log of 0.1 is equal to positive t over RC. Now Warson's going to laugh at me. Oops! You know what? That negative stays. Ah! Now he's really going to laugh at me. Okay, so the negative stays there. Now, if we solve for t, check it out. Once again, we've got r times c times the natural log of 0.1 is equal to negative t. Now, the natural log of 0.1 is going to be a negative number. Multiply by RC, and check it out. The thing that's kind of cool here is that R is 200 times 10 to the third ohms, 200 kiloohms. C is 50 microfarads, so 50 times 10 to the minus 6 farads. When we multiply those two guys together, what do we get? This is like 2 times 10 to the 5th, and this baby here is 5 times 10 to the negative 5th. The 10 to the negative 5th and the 10 to the 5th are going to cancel out and give us 10. So we have basically negative 10 times the natural log of 0.1. So the answer is like 23 seconds. So punch that baby out and you find out, hey, it's in 23 seconds this capacitor will have reached 90% of its maximum charge. The next question asks, okay, what is the energy stored in the capacitor at time RC? Okay, again, there's some tricks, so watch what I'm up to here. I hope all that was on camera. I keep forgetting to look up at the video monitor. Oh boy. Okay, so U is equal to 1/2 Q times V. Or we could say Q squared over 2C, however we want to write it. Well, let's think about this. At t equals RC, we already showed that this is 10 seconds. Okay? Q naught, as we said before, is equal to C times E. All right? That kind of makes sense again. C is charge per unit volt, and therefore charge equals C times V. We're just calling it EMF right here. So this equation here kind of shows that that equation is probably right. All right. Now, if we check out this equation, we go back to the equation for a charging capacitor, we find out that when a capacitor is charging, okay, in other words, we put RC in for t, at time t equals RC, Q will be 0.632 Q naught. If you don't believe me, try it out. Get this equation going, put an RC in for t, and solve it. So, if that's the case, then we can replace this guy with C times E in order to find Q. All right. We know the capacitance, so we're cooking with gas. That means U is equal to 0.632 times C times E squared all over 2C. Okay, give it a try. Put C in there, that's 50 microfarads. Put E in there, that's 200 volts. Change the microfarads to farads, by the way. On the bottom, we've got 50 microfarads again, but be careful, the top is squared. This is Q squared over 2C, so this is Q squared over 2C. If you punch it through, you're going to get 0.4 joules. All right. What's the power loss at that time? Okay, well, that's part C of your example. What's the power loss in the resistor? You say, okay, power loss in a resistor is equal to I squared times R. Okay, so what's the current like at T equals RC? Well, we said that the current is going to be 0.37 the initial current. Okay, well, we can find the initial current because you kind of think of this when this circuit is initially closed. The capacitor is not going to stop things too much. In other words, this capacitor is like an empty bucket. It's going to fill up really fast. So when we turn on the switch, when we flip the switch and make the connection, current's just going to flow like mad through this thing, and it's going to act as if it's just a resistor and a battery. Now that's only going to last for, you know, a few tenths of a second, but at the very beginning we can say, hey, the current I equals V over R, or in this case EMF over R. Okay, so the maximal current we're going to get is 0.37 times EMF over R. I hope that made sense. Okay, so we've got maximum current and we've got the resistance. All right, so if we do this, we're going to say, okay, 0.37 E over R squared times R. So go ahead and punch that through. E again is 200 volts. R is 200 kiloohms. See if you get 2.7 times 10 to the negative 2 watts, just like in my notes. Okay. The last two deal with the energy stored in the capacitor. Okay, what's the final energy stored in the capacitor? When this thing has finally made it to its maximal charge, how much? And you can see my work there. We just say, hey, voltage is work over charge. So put it in the language of this particular circuit, EMF is equal to work over charge. So work equals Q naught E. All right. Q naught is C times E. So again, we have these values. We know the capacitance. We know the EMF of the system. Turns out to be 2 joules. Okay. The total work done by the battery to charge it from one plate to the other. Okay. All right. That's part D. So part E says, all right, what's the final energy? So I kind of had those backwards a second ago. The final energy is going to be Q naught squared over 2C. Okay? And as it says in my notes, 1/2 C EMF squared. We've got the EMF, we've got the capacitance. We say, hey, look, it would do 1 joule of work. Or it would, I beg your pardon, it would store 1 joule of work. Well, wait a second. The battery did 2 joules of work, but only 1 joule of work is stored on the capacitor. Part F, what's the total energy lost in the resistor? So where did that 1 joule of energy go? Oh, the resistor ate it up. It turned it into heat. So part F is kind of easy. We just say, hey, it's 1 joule. Conservation of energy. the battery does 2 joules of work, there's 1 joule stored on the capacitor. That's where the other joule went. Okay? So